Yeah. Okay. All right. So everybody, this is Zach, or Zachary, or Zach. Either one. Okay, we'll go with Zach. Less syllables. Gallegos. As a master's student here at UNM, his current research deals with landing site analysis for Mars and Earth-based analog site evaluation. He can tell you what that means if you want. He received his Bachelor of Science in Earth and Planetary Sciences in 2010 from here at UNM. And where he did research on the Mars Science Laboratory or Curiosity instruments, culminated in a multi-day rover simulation for MSL Sciences. After graduation, Zach spent time at LPI as a lunar exploration analyst, where he took part in a major effort to identify the best localities to send humans back to the moon. No small undertaking, by the way. There's some fabulous work that those guys did. His latest accomplishment in the planetary science field was selection to the Mars 1 mission, which plans to land humans on Mars in 2024. Down from a field of over 202,000 applicants, Zach is now in the third round of selection and part of the top 700 candidates.
Mars, huh? Wow.
And he's also got his poster he's presenting next week out in Pasadena at the Mars 8 conference, so you can see how posted one way anyway, a poster we put together. But he's going to talk to us now about Mars tectonics and volcanology.
Hey everybody, my name is Zach Gallegos. So, a little bit about me other than that. I first started getting involved in geology when I was really young.
Can you get a little bit closer? It's kind of noisy back here, the air that's trying to run and not quite being successful.
I first got interested in geology when I was really young, and I always knew that I wanted to be an astronaut. And so I figured going in geology would be the best way because you need people to study the rocks when you go to other planets. So that was my main thinking, why I'm here today actually. So I'm going to talk to you about Mars, tectonics, and volcanology. So first of all, here is a map that you might have seen before. It's a molar. That's it's a topography basically. They shine the laser down at Mars, and the laser comes back and tells you how high the surface is. So as you can see, there are a few things. Lots of craters. A lot higher elevation in the south than in the north, and very pronounced features in this region, things like that. And I'll come back to this map every now and again. So first of all, plate tectonics is something that we do see on Earth. And it's what happens when the lithosphere is actually sliding above the asthenosphere, which is just the upper part of the mantle. And so the theory was proposed and, well, not accepted until later, but proposed back in the early 1900s. And you can see here a diagram of all of the plates of Earth, the major ones, divided. And you can see they're sort of resemblant of, their continents. But the question is, does plate tectonics exist on any other planet? So a little bit more about plate tectonics. It recycles material back into the Earth, or into a planet, and it also regulates the atmosphere based on what kind of stuff it's taking down into the Earth and how much stuff it's pumping back out. And so what happens is you have these convection currents, and where it comes up in the mantle is where you have divergent plate boundaries, and where the convection is going down, you're pulling plates down into the mantle, subducting them. So here's another view of Earth, and you can see here South America, North America, all the continents. And all the blue and red lines are actually plate boundaries. And you can see all these little red dots in here are volcanoes. And one thing that you may notice is along the plate boundaries you see a lot of volcanoes. And so a little bit about the difference in colors in those lines. The divergent plate boundaries, which were the red, is what happens when the plates spread apart. So that convection in the mantle is coming up and pushing the two plates apart. And in a convergent plate boundary, where the convection current is pulling the plates down, you have this plate moving against this plate, and one eventually goes down under the other. And then another type of plate boundary is a strike-slip fault, and that's where the plates run next to each other like this. So divergent plate boundaries. A major one on the Earth is the Mid-Atlantic Ridge. And as you can see, there is a big split in the crust here, and all this material is upwelling and pushing these two plates apart and just forcing new material to the top every day. Another one that you see actually in continental plate boundaries, or in continental plates, is the East African Rift and the Rio Grande Rift. And so you see here, it's not coming up in the middle of the ocean, it's coming up in a continent. And convergent plate boundaries, you have the different kinds, oceanic to oceanic, which is represented up here. It's sort of like in the Marianas Trench. You have oceanic to continental, that's like in the Pacific Northwest where you see all those volcanoes out there. And then you have continental to continental, like in the Himalayas, where you have the Tibetan Plateau and the huge mountain range. And the last one, strike-slip fault, is like the San Andreas of California. And so it runs like this, and one side is moving this way, the other side's moving this way, and that's what we call, if you're looking across the plate and motion is to the right, that's what we call right lateral. And if you're looking across the plate and the motion's to the left, that's called left lateral. So as far as plate tectonics on Mars, you don't really see much of anything. As far as global tectonics, there's lots of ideas. It might just be that Mars is too small. It's smaller than the Earth. It might be that it's composed of different stuff. Maybe it doesn't have as much water as the Earth. We do see small-scale faulting and also big-scale rifting on Mars. So there are tectonic forces, just not full-on plate tectonics. So we know so far. So looking back at the topography of Mars, you notice that the difference between these two images is the biggest one to me anyways, is the amount of craters on Mars versus Earth. On Earth, you'd be pretty hard-pressed to find any craters visible to space. There are a few, but on Mars, they're very abundant. And what that means is basically everything on Mars is older than everything on Earth. Because when you're looking at the age of a planet, you use crater counting. And so the amount of craters per unit area gives you an idea about the relative age based on other parts of that planet. So for instance, this lower southern part of the planet has a lot more craters than this upper highlands part of the planet. So we say that the highlands is actually younger than the lowlands. Or it's been resurfaced since deposition. Another thing that you can notice about the Mars map is this big area like I talked about up top. And you see areas of low elevation on Earth like that too. These are ocean basins. And lots of people like to imagine that this was a big ocean basin, there were plate tectonics maybe just stopped. But in fact, nowadays we recognize that it was probably a huge impact. A big asteroid came and took out a big chunk of the planet and left a low-lying topography. And also, people depict Mars with an ocean of water in the top. And since it is a depression, you might think that water would flow there. So if Mars ever did have an ocean, it probably was there. And another thing is that when you look at the Earth's continental to oceanic lithosphere, is the boundaries are very sudden. The drop-offs to the ocean plates are very pronounced. Whereas up here, it's very slow sloping. So we don't think it's the same mechanism, even though it might look a little bit alike. So I heard you guys talking while I was out in the hall about magnetics. And Mars seems to lack a magnetic field as of right now. In the past, it may have had one, and we see magnetic anomalies and things like that. And so what happens on Earth is that in a rift zone like here, is you have new material going up to the surface. And when the poles are aligned to the north, all of the magnetic stuff in the lava is going to be pointing to the north. And when the poles are aligned to the south, all the magnetic stuff is going to be aligned to the south. And so that's what this is showing. So here's normal times pointed north, and here is southern poles, northern poles, southern poles, like that. And so when you go into the mid-Atlantic ridge or other places, you can actually see those bands. And so the reason that Mars doesn't have a magnetic field is also not known yet. It may be one of these three options. Maybe the mantle just cooled too quickly, and so there's no convection. Oh, so a magnetic field is produced when you have a solid iron core and a molten liquid core rotating around it. Basically produces a dynamo. And so on Mars, we think that either the core cooled too quickly, or the outer core shrunk, and so it couldn't provide the necessary convection, or it has to do with plate tectonics actually, and plate tectonics on Earth is what's fueling the mantle convection, giving us our magnetic field. And so here's what the magnetic anomalies of Mars look like. And so you can see here some banding, which is north-south, north-south. So a lot of people have said, look at that, that's evidence of plate tectonics. But it's not on the same scale as we see on Earth. So early on, Mars may have had some plate tectonics going on, which is why we may see this banding. But as far as now or any time in the recent past, no plate tectonics. So I was talking a bit about the interior of Mars earlier, and so here you can see it's actually a lot smaller than the Earth. And we don't actually know the structure of the interior of Mars because we've never sent geophysical instruments, no seismometers, things like that. But actually there's a mission that's being launched soon that has a seismometer on it. So we should be getting back some data soon. So faulting is tectonic movement. And there are different types of faults. And here you can see a good representation in the field of a fault. You can see this line matches up here and then back up here again. So that would be what we call a normal fault. And that's when things are pulling away from each other. And when that happens, this area down drops, just like this one here. And in a reverse fault, it's compression that's driving the forces. So this actually goes up compared to this. And here again, strike-slip faults, left lateral, right lateral. One's moving just sideways against the other. Oh. And so faulting on Mars, we do see it. It's not as pronounced as on Earth. Here's a very long thrust fault on Mars. It's about 400 kilometers. And we see lots of normal faulting in, say, Valles Marineris. And there's also been a proposed strike-slip fault in Valles Marineris. You can see this hemisphere is supposed to line up with this hemisphere right here. This isn't a widely accepted theory, but it's one that's out there.
Could you, just to make sure everybody knows what Marion Valley is, could you go back to the mole map and show us?
Yes, I will. So I'll go to the front.
Sorry.
It's okay. So this right here, this feature, is called Valles Marineris, and I will talk about that in just a second. So back to where I was. Let's see. Okay, so again here, Valles Marineris, and you see lots of faulting around this particular area of Mars, which I will talk about later, the Tharsis Bulge. And here you see lots of faulting also, basically things being pulled apart, rifting. Okay, so Valles Marineris, like I said, is this feature on Mars right here. It's a giant tectonic crack in the crust. It is 4,000 kilometers long and 200 kilometers wide at its widest and up to 7 kilometers deep. And it is the largest canyon system in the solar system. So it takes up nearly a quarter of the planet's circumference and is 9 times longer than our Grand Canyon is. So pretty big. And here's a nice image of it to show you. And I like to show this one too, just to show you the actual scale. Thing's huge.
And this is not even the end of it. It goes off in here a little ways. So now I'm going to talk about volcanology. And that is the study of volcanoes. And volcanoes are what brings new material to the surface in the form of lava or gases or ash, things like that. So we know a lot about the volcanology of Earth because we've been studying it for quite a while. Most volcanology happens at plate boundaries, divergent plate boundaries, convergent plate boundaries. This is an example of one that happens at divergent plate boundaries, a fissure volcano. It's where there's just a crack and lava finds its way to the surface. A shield volcano is a type of very gently sloping volcano. And this is because the material that it's erupting actually isn't very viscous. So it's able to flow out for long distances. Dome volcano is actually the opposite. It's not very viscous, so it forms these thick dome-like volcanoes. Same thing with composite volcanoes. And caldera-forming volcanoes are the big ones that are very explosive. Lots of gas involved in very viscous lava. So the volcanology of Mars, there's no visible plate tectonics. And so there's a lot of shield volcanoes. And so what happens with shield volcanoes, they usually form at a hot spot. And let me see. A hot spot is like Hawaii. That's where there's a volcano in the middle of a plate. And the Pacific plate's a big plate, so there's not a lot of movement around. And so in the middle of the plate, there's a zone of weakness and high temperature, and all the magma finds its way out of there. And so on Mars, we have mostly basaltic compositions, but it goes from ultramafic to dacitic, and I'll talk about the difference between that in a minute here. And here is a diagram of the volcanoes of Mars. You can see the large shield volcanoes in purple in this region, smaller shields over here, lava flows and volcanic plains, things like that. So as far as the mineralogy of Mars, like I said, it's mostly basalt. And the basalt from Mars is actually different than the basalt from Earth. So we can take lots of basalt measurements and plot them on a graph of plagioclase and orthite versus pyroxene and olivine. And we can see that Mars is a lot different from Earth. Earth plotting here, Mars here, the moon there. And we can also plot them on a graph like this, which is showing silica content, which is important for volcanics. Because the more silica content you have, the less viscous, the more violently eruptive. And let's see. So why do we mostly only see basalt on Mars? It's because of the lack of plate tectonics. Because in convergent boundaries down here, where you have a subducting plate going through lots of continental crust, it has lots of time to collect other material that's along the way. Whereas here in a hot spot like Hawaii, it doesn't have a long ways to go, and especially not in the divergent plate boundaries like in the Mid-Atlantic Ridge. It's just basically going from the mantle to the crust. But when there's lots of crustal involvement, you have high silica content, and it's more explosive. And so with no tectonics, here's a mantle plume being represented here. And this happens on Earth just like in Hawaii, like we said. But in Hawaii, the plate is moving this way. So we have these volcanoes erupting like this in succession. And pretty soon this one will go dormant and a new one will pop up right here as the plate moves. But on Mars, with no plate motion, you have all of this lava just stacking up on top of each other, just over and over again, which creates these huge shield volcanoes. And I like this picture a lot because it shows one thing, that the biggest mountain in the world is not actually Mount Everest. It's the tallest mountain in the world. The biggest mountain is actually Mauna Loa in Hawaii, rising about that high, and then Everest about that high. But then you have behind it the biggest volcano in the solar system, Olympus Mons. And you can see it's a pretty big difference in height there. So now I'm going to talk about the different types of volcanoes on Mars. The montes, or singular mons, are large shield volcanoes, generally sloping less than 6 degrees, so they're not very steep at all, meaning their lava wasn't that viscous and was able to run. You have the tholi, or tholus, singular, which are smaller, more dome-shaped volcanoes. And we can tell they're older because they're covered by subsequent lava flows and other sedimentation and things. And we don't really know if they're different material than the mons, or if it was just less material that was erupting. We don't really know what makes a difference. And patera is a term given to small volcanoes with larger calderas than the tholi. As you can see here, pretty big central caldera in this volcano here. And patera literally means shallow drinking bowl. And so on Mars, when they start naming these types of volcanoes, they just want to name them after something it resembles, not after something on Earth, because they might be wrong in the future. So it's safer that way. And let's see. So these probably represent larger volcanoes that were just buried by sedimentation and other lava flows. It was saying that this one is probably actually 4 kilometers high. It's just we can't see it all. Rootless volcanoes, or pseudocraters, are basically, they don't have a magma source. It's what happens when a lava flow is flowing over a body of water, either subterranean or on the surface, and that water is actually turned to gas because of the heat, and an explosion happens and creates a crater, like this one you see here, or these ones. So now we have different volcanic provinces on Mars. The biggest one here is called Tharsis. And over here, Elysium, and you have the Syrtis Major region, the Highland Patera region, and up here, not labeled, is Arabia Terra. And so what you'll notice is this one has basically the biggest volcanoes, and I think I talked about that now, yes. So it's the largest, here it's kind of mislabeled. People say that this is Tharsis, it's the Tharsis Bulge, but then we say that all the volcanoes around here are actually in the Tharsis volcanic province. And so the whole province averages about 7 to 10 kilometers above the planetary datum, so above 0. And they represent some of the youngest flows on Mars. And here's another cool depiction. I like these scale things. It shows you actually, here's Olympus Mons right there, and the 3 Tharsis Montes. So pretty big volcanoes. So Olympus Mons is the largest volcano or mountain in the solar system. 24 kilometers high, 500 kilometers in diameter, a slope of around 4 degrees. And it actually, inside here, has 6 different calderas. So they can actually see which one erupted first compared to the other one based on stratigraphy. And so Alba Mons is also in Tharsis, but it's a little towards the north, and some people argue that it's a different region. It has very, very low slopes, 0.5 degrees, so it's basically not even a hill. 1,600 kilometers across, so it's very expansive, and rises 3 kilometers, only 3 kilometers above the plains. Elysium is second largest volcanic province, and its biggest volcano here, Elysium Mons. And you have Hecate Tholus up here and Albor Tholus right here. Syrtis Major, which is a little hard to see. Here's the Isidis Basin right here. Syrtis is this region right in here, and you can see 2 calderas. And it is 1,200 kilometers across, so pretty big also. Only 2 kilometers high, so very gently sloping also. But in this area, we see more silica-rich rocks, dacites and granites. And then there are the Highland Patera, which are located around this huge impact structure, the Hellas Basin. And people often say that this volcanism could be triggered by the actual impact itself. And also Arabia Terra or Arabia Terra has low relief patera, and it's in this region. And here's one example of the small patera. This is Eden patera, I think. And Arabia Terra is basically just this whole area right in here. Any questions?
The big rift valley, whatever that is really close to the largest volcano.
That is what I forgot to mention. Thank you. So yes, what happened was the Tharsis Bulge was pushing up, and basically the Valles Marineris just was splitting apart. And you can see it's pretty much, perpendicular to the bulge. So that's basically the theory, is that when all this volcanism was happening and pushing up the crust just split apart. A lot of people like to think that it was made by water, but there's definitely evidence of water flow, but it's mostly a tectonic fissure. Yeah.
Is that like a volcanic mar?
So yeah, a mar volcano is when a magma chamber comes up and interacts with groundwater. So I think what they're saying with pseudocraters, though, because there are mar craters that are proposed on Mars. Pseudocraters, what happens when you have a lava flow going over a standing body of water, or very close to the surface water, and as that builds up heat and gases, it just explodes out the top of the lava.
People were talking earlier about Mars and the internal structure and magnetism. You covered that pretty well, but do you have any questions remaining because of that? Or any questions?
Just a question about, obviously, there's not sea level on Mars, so what do you base?
So
3 kilometers, 5 kilometers?
that's a good question, and it actually makes a little more sense than it does here on Earth, because here we base it off of sea level, which is good, but on Mars, when we have this, so this area right here between the southern highlands, the old southern highlands, and the low northern lowlands, the young stuff, right here along the border, and it comes into the Isidis and into here, is where I think it's the triple point of water, or where it's some interaction with water, where all 3 or 2 of the boundaries between the phases of water interact. And so that's what you call the planetary datum. And it just so happens that it lies on the border between the highlands and the lowlands. Yeah, basically it has to do with pressure and temperature.
Oh, okay.
So,
That does make more sense then.
yeah, they're just saying 0 is that line.
So for a planet to produce a magnetic field, you have to have a solid metal core.
Uh-huh.
You have to be iron, and then you also have to have a liquid.
Liquid outer core. Iron can be pretty magnetic. So I haven't actually thought about planets with other kinds of metal cores. Like in the Earth, we have an iron nickel core. On Mars, they think it's more of an iron sulfur core based on densities, things like that. And yeah, the magnetism, you have to have a dynamo. And for that, you have to have something rotating around something else. And so you have a solid core, liquid outer core, and the rotation produces a magnetic field.
I never heard what you said after that about another possible cause of Earth's magnetism, which was the convection.
Oh, so that's just maybe not another, it might just be something that helps it along. So when you have slabs going down into the mantle, it's actually cold compared to the mantle, and it creates convection because cold and hot. And also a lot of the convection comes from the outer core. The outer core is actually making the mantle convect.
So the subduction of the mantle, of the crust into the mantle, might be helping the circulation in the outer core?
Might be helping the circulation everywhere.
Okay.
That's something that I've heard.
So you weren't saying that the magnetic field is created
No,
And
yeah.
because of convection.
Yeah, thanks for clearing that up.
Well, I misunderstood.
And there's still a lot we don't understand about all of that, right? Because we really don't understand why Venus doesn't have one, right?
Yeah, and Venus is a whole other story because it's really hard to study. Yeah, and so far we only have the Earth with a magnetic field and plate tectonics, so this is what we have to go off of.
You mentioned Olympus Mons as being the largest volcano in the solar system.
Yes.
Correct me if I'm wrong. Didn't I just hear sometime this last year that they found a volcano in the North Pacific that they believe is larger than Olympus Mons? Anybody else hear that?
I haven't heard that. It would be harder for me to believe just because of the actual size of Olympus Mons.
Yeah, no, I've always heard, thought of Olympus Mons as being the largest.
Something around like 85,000 feet.
Yeah,
And so, yeah, Mauna Loa is bigger than Everest.
right.
And that's because you don't see most of it because it goes below sea level.
Before, right.
Yeah. So I'm going to have to look into that.
Yeah, I thought I remember seeing some research that someone has discovered a volcano in the northern Pacific Ocean that they believe is larger than Olympus Mons. But I can't remember exactly where I read that research either.
Yeah. I'll have to look into that.
We got a few minutes. Do you want to come just talk about your poster?
Sure, I could do that. So, my work involves mostly this site right here, which is in the Arctic. It's at a place called the Houghton Impact Structure. It's an old impact structure, I think 24 kilometers in diameter. It's of Eocene age, and so that means it's 39 million years old. And so what we were doing here is we were collecting rocks from this hydrothermal vent. And so when we go to other planets looking for astrobiology stuff, other forms of life, we want to look at places that have the best opportunity to produce it, like hot springs, where you have water and heat. And so we went to this hydrothermal vent and collected a bunch of rocks. And I turned these rocks into what we call thin sections. And a thin section is a very, very thin slice of rock. And so thin you can pass light through it. And you do all kinds of tests on that. And what I did is I shot these thin sections with the laser that's on the rover right now. And then I also tested it with the XRD instrument and the APXS instrument on the rover. And so I put all that together along with the images of the samples and also this electron microprobe work into a simulation for the Mars scientists for the rover. And here you can see these colorful maps are actually representing different elements. So this map corresponds to this image, and you can pick out some of the grains in that image and see which ones are rich in, say, silica or iron or things like that. And so I'm going to Caltech and JPL next week to present this research. Just printed it today, hot off the presses.
And you made some for us, right? I'm kidding.
I can make some copies.
That's impressive.
And the bigger picture of this, the way that that this fits into our understanding of Mars and the Earth, is because.
So when we want to study Mars, but we can't exactly go there, we study analog sites on Earth that look like Mars. And so what we do is we test those sites with all the instruments that we take to Mars. And then we look at the sites on Mars and see how they're similar, how they're different, things like that.
And so will your results help to confirm or better understand some of the results that ChemCam, for instance, is seeing on Mars?
Yes, because what I did is I shot all these with the ChemCam, but not only did I do XRD and APXS, but also microprobe work. So I can actually go in and check to see that all of the ChemCam things are working correctly.
And so yours can help to verify
Exactly.
what they're seeing over there.
That's the job. Any other questions?
Are there big gravity anomalies on Mars?
There are gravity anomalies. I haven't actually looked into it a lot. I don't know. There are, though. I assume there's a big one near Tharsis, and probably another one in the Hellas Basin, and probably another big one up here in the northern lowlands.
We have a scientist at LPI, Walter Keeper, who studies things like gravity anomalies. We can see if maybe he has a couple words to say.
Mm-hmm.
Any other?
Completely off topic.
Yeah.
Because you said you were interested in doing this since you were very young.
Yes.
So if you think about middle school and high school,
Yes.
did you have any any science teachers that made you more interested, any science teachers that made you maybe less interested, and what did those teachers do that made you?
Absolutely. I had a teacher in high school from 9th grade to 12th grade, Ms. Durkin, and she was my astronomy and geology teacher for my first semester and second semester, and after those semesters I was her teacher's aide every semester because I already knew I liked rocks and space because, I mean, New Mexico is a great place for rocks and looking at stars. And she was really energetic and just was excited about teaching us this stuff and showed us cool things like this. And she did inspire me.
Okay. How about anybody in the other direction? It was like, all right, I'm going to give up because of that.
Yeah, I've had a few of those.
So what, don't tell me their names, just like what did they do that turned you off? What was that? What should we not do?
What should you not do? Don't confuse